All right. We're on medical applications of nuclear physics, aren't we? Yep. Okay, so let's talk about some things, I suppose, here. So, one of the common uses of radioactive isotopes in medicine is imagery. And in order to use radioactive isotopes for imagery, you have to somehow get the radioisotope into the place connected to the thing that you want to know about. And that can be done by injection or by breathing it, or by actually placing the material in the body in another way. But really what you're doing is you're selectively putting this material that is radioactive inside of the patient and then watching as the radiation comes out. See where it comes out, how much comes out, depending on what you're trying to learn, depends on what you're trying to do. But the different materials, you have to have materials that will go where you want them to go, stay where you want them to stay, and show you what you want to see. Those things are all important. And so they've done a lot of studies with materials, and they know exactly what materials work for what things best. This is what this table is all about here at the very beginning of the chapter. It shows us a bunch of the different materials that are used in radioactive isotopes. And these radioactive isotopes are just made by sticking these materials inside of a nuclear reactor, and then they become radioactive as they absorb neutrons from the neutron flux of the reactor. So, here we have brain scan isotopes. These are used for different types of brain scans and different types of situations. And they've got the type of material and then the activity. So this tells you in millicuries how many decays they're getting. So for technetium, 99M, 7.5. Indium, 113M, 7.5. But in PET scans, which are the positron emission tomography scans, you can use carbon 11, nitrogen 13, oxygen 15, and fluorine 18. And they have higher activities. In other words, they are decaying more per second, 20, 20, 50, and 10. For lung scans, they're using technetium, just like this one up here, except in this one they're using one that has an activity of only 2. And how do you have one that has an activity of only 2 versus one that has an activity of 7.5? Well, one that has an activity of 7.5 is newer than one that has an activity of 2. This one's been sitting around a while, so its activity has decreased. Because remember that curve we saw, where the activity starts off high and then it dies off, right? So this one only has an activity of 2 when they're doing a lung scan. They don't want as much, they don't need as much radiation coming out to make that image. And then the xenon 133 here again. Oh, they don't use it up here. For the lung scan. For cardiovascular, they're using iodine and technetium. Cardiovascular arterial flow, so this is essentially flowing through the arteries of your body. They're using thallium and sodium. Two different kinds of iodine for thyroid. Liver, using gold and technetium. Now, the reason they use different ones is because, and colloidal, by the way, means that it's suspended in liquid. But the reason they're using different stuff here is because this, for example, in thyroid, the thyroid absorbs iodine. That's one of its purposes actually is the thyroid gland is to absorb iodine. And if you can get something into an organ easily, and it can be radioactive, then you can use it to scan there. So iodine is the perfect choice for the thyroid because it already gets absorbed by the thyroid. In the liver, you can get gold and technetium in there pretty well. Bone scans, you're using strontium and technetium. And then in kidneys, you're using lead and technetium. So technetium is obviously a very useful thing. The M up here means that it's not entirely stable, it's metastable. And so here we're going to use what is called an angular camera. And we actually saw one of these when we were looking at when we were in the museum the other day, in the section on black holes, where they had a telescope that was focusing X-rays. In order to have a camera a really good, effective camera that can see different things at different depths inside of your head or your body, you need to have the ability to focus things. But gamma rays just do not focus things very well. Gamma rays don't focus very well because they go through things. You know, you can't use lenses or mirrors to focus gamma rays because they'll just go right through it. They won't turn at all hardly. But you can use lead to collimate it. And to use lead to if you use lead to collimate, you get the gamma rays that go straight through these lead. They're kind of like lead tubes, you can think of them as. The ones that go straight through don't get blocked, but the ones that go sideways kind of get absorbed by the lead and don't get seen. And then over here you have these detectors, which are essentially just photomultiplier tubes, but you have a bunch of them at different places so that you can see different detections from different positions, so that you can get somewhat of a focused image. And then they put together the image using a computer. So this one is this spatial, single photon emission computed tomography, which is similar to CM or CT, just CT, which is the computed tomography, or CAT scan. But this one uses instead of using light or X-rays that are a little lower energy light, this one is using single photons of gamma rays essentially. So it's using this guy here. It's using this kind of technology here with the angular camera. And this thing, one of these things emits, the other one, and the other side detects. And the reason for this big ring here is to rotate this thing around. This thing can rotate around at different angles and get you different slices through the body and give you that tomography. Anytime you see the word tomography in medical situations, you can almost guarantee that they're rotating some imaging equipment around the body, taking pictures from different angles, and then using a computer to put all those things together. So CAT scan is a tomography, SPECT is a tomography. You have another one down here, the PET scan, which is positron emission tomography. Same kind of idea. Here they're showing the idea of the positron emission tomography of gamma rays that go through, but they create, they create positrons in the process. And these positrons will go in and, well, sorry, that's backwards. The machine creates the positron through an acceleration process. So it has essentially an accelerator that creates positrons. And as the positrons come in, they actually meet up with an electron in your body and annihilate with the electron to become pure energy. And that pure energy is in the form of the gamma rays which come out, and then the gamma rays are detected by photomultipliers out here in all directions. They don't just come out one direction, they come out in all directions. And then they can image things in your body using those gamma rays that come from your body. So anyway, lots of many various ways to use these nuclear science ideas to do imagery in medicine. Okay, so what's the downside? The downside is damage. This radiation is often high enough radiation, if not nearly always high enough radiation, to cause damage to your cells. And in order to determine what kind of damage is being done, lots and lots of people did a lot of research and put themselves in a lot of danger. And most of them died from some kind of radiological sickness or another. But eventually they came up with some ways to measure the amount of radiation coming out and also to determine if that radiation amount is going to be dangerous. So here we have one of the units that we use for measuring a dose of radiation. So 1 rad is equal to 0.01 joules per kilogram. So the joule is the amount of energy coming from the radiation itself, and the kilogram is how much of the body is exposed to it. So it's kind of a funky mixed unit, you could think of it as, where you have energy from one thing affecting mass of biological matter in another thing. But here is an example of how we use that. We have a 50 kilogram person is exposed to some ionizing radiation over the entire body of the person, so that includes all 50 kilograms, absorbing 1 joule of energy. So then you get 1 joule per 50 kilograms, which is 0.02 joules per kilograms, which is 2 rads. So remember, it's 0.01 joules per kilogram is the 1 rad. If you do 1 joule of ionizing radiation absorbed only in the forearm, which is 2 kilograms, then it's 50 rads. So you can see where the mass makes a difference. If you concentrate it in a certain amount of mass on the body, the amount of radiation exposure that you get or the dose that you're getting is much higher. And it's well known what doses of radiation the body can handle in a lifetime or over time. And so they try to track these things. They also have another radiation which is not used as often. The rad is used very often, but we also use the gray for the SI unit, which is 1 joule per kilogram, so it's 100 rads. It's 100 times more than 1 rad. So it's not used very often, but it is technically the SI unit for dosage. So the next unit is the REM, which I always forget what this stands for, but it's right here, the Röntgen equivalent man. Right? So Röntgen was the guy that discovered the X-ray. And essentially what this is we multiply the number of rads that you have by a relative biological effectiveness, which essentially has something to do with how the particular radiation is going to I think, penetrate the body because different types of radiation penetrate the body differently. So here is you have gamma radiation, which is of course your light radiation, right? And then you have the alpha radiation, which is the alpha particle radiation, right? And you have all these cells lined up in here, and you're seeing what's going on with ionization. You have ionization in this first cell here, a little bit, but you have a lot of ionization a little bit further in. And with the alpha radiation, you have a lot of ionization at the beginning, and then some ionization further in, and some ionization further in. And you get different kinds of essentially different kinds of damage can be done. Is really how you can see it. But this is something that is measured by that RBE, or that Roentgen equivalent. Sorry, not so the RBE, which is not Roentgen equivalent. That's the relative biological effectiveness. And they often use this. They often call it the quality factor as well. So we want to go to a table to determine how much damage you're getting from different kinds of radiation. So X-rays have an RBE of 1, gamma rays RBE of 1, beta rays, which are the electrons, an RBE of 1. Beta rays that have less than 32 kilo electron volts, 1.7. Neutrons, slow neutrons 2 to 5, fast neutrons 10 to the body, 32 to the eyes. Protons the same. And then alpha rays 10 to 20, heavy ions 10 to 20. And then so yeah, so then we come down here to the sievert. So we've gone from, let's start from the beginning really quick again. We start from the rad, which is the radiation dose unit. That's how much dosage you get, and that's energy per kilogram. Let's actually go a little bit further. Let's go back one more page. I just want to do a step through of all these different units really quick. So the first thing is the activity, which is the millicurie, which is measured in becquerels. Remember, becquerels are, if you remember the last chapter, becquerels are decays per second. So if you have an atom that is going to go through a decay and release some kind of radiation, and it does it every second, then you have 1 becquerel, right? This is 1 millicurie is 3.7 times 10 to the 7 becquerels, so it's a lot more. 37 million becquerels is 1 millicurie. This is activity, and this is the number of decays per second. How actively is a sample actually decaying? So that's the first unit, is the curie and the becquerel. And then we move on to our next unit, and these all have to do with how much energy is being absorbed by the body by these radiations, by any type of radiation. So this one doesn't really take into account the individual radiation. It just takes into account how much energy is absorbed by the body in joules per kilogram here, and that's the rads. And then we go on to the gray, which is the 100 times that. It's the same. It's measuring the same kind of thing. Then we go into the rem, which is different. So this tells you how much energy the body is absorbing. This one tells you how much damage the body that is being inflicted on the body by that energy. So you take the energy that's being put in, and you have this quality of the energy, the quality of the quality factor, or the biological effectiveness of that radiation. And so if it gets bigger, of course, you get bigger damage. And here is the table of those, as you go from small damage to big damage, right? And then So here here we have a table of those. The activity is the Becquerel and the Curie. The absorbed dose is the gray and the rad. And then the dose equivalent is the sievert or the rem. Right? The gray is equal to 100 rads, the sievert is equal to 100 rems. And then we take a look at what kind of damage is done at different levels of dosage. So if you have 0 to 0.1 sieverts, there's no observable effect in your body. There could still be a significant effect, but you can't really see what's going on. So it could be some damage at the cellular level, at the DNA level. Could be the beginnings of cancer, but you're not going to see it right away. 0.1 to 1, you'll immediately see a moderate decrease in white blood cell counts. So it affects the blood system first. Those white blood cells get killed off, and your ability to replace them gets moderated a bit. 0.5, temporary sterility, 0.35 for men, and 0.35 for women, 0.5 for men. Now what this does, the reason that this does this is because this ionizing radiation has a tendency to kill off fast reproducing cells first. So things like the white blood cells in your blood are fast reproducing cells, so those get killed off really quickly. And also your reproductive cells, which are fast reproducing cells. Now, and they're also, for women, they're not necessarily fast reproducing, but they're very delicate cells. For men, they are fast reproducing, and that's why it affects men more. And then you have a significant reduction in blood cell counts, nausea and vomiting, but it's not really fatal from 1 to 2 doses, a dose of 1 to 2 sievert. 2 to 5, it starts to become extremely dangerous at that point. 2 to 5 sieverts, and you're getting sick, you're losing your hair because, again, that's another fast-growing cell, and you're getting, your blood is damaged to the point that it can't recover, your liver can't replace it, and it can't recover, and your liver is getting damaged because the liver is a fast replacement cell thing. You're hemorrhaging on the inside of your body, so you're starting to swell as you're bleeding out on the inside, and you're getting really, really sick, and you're very likely to die. 4.5, 50% lethal. There are not very many sicknesses that are 50% lethal. Only a couple of them. And 32 days of exposure is pretty much the limit that you can handle at that level of dosage. Then between 5 and 20, you're almost guaranteed to die. And greater than 20, you're going to die within just a few hours. It's going to essentially destroy your brain and your nerves. So this is something that was studied ad nauseum. They studied this and studied this and studied this during World War II and post-World War II so that they could figure out how to safely deal with radiation. The biggest reason for this is so that they could actually harness radiation and use nuclear power. Without this information, they could have never, ever developed nuclear power safely. They had to figure out what was dangerous, what was not. And so they sacrificed a lot of lab animals to this. Did a lot of studies to understand this. So, what do we do to protect ourselves? Well, one of the things we do is we limit our radiation dosages. So anybody who works around radiation has to wear a badge. If you go downstairs to, if you went downstairs to the dental office downstairs, the dental room, before they put in their new digital X-ray machines, they had to wear a badge all the time that was essentially just a piece of film that was designed to be exposed to show how much exposure the operator of the X-ray machine is getting. And anybody that uses medical equipment that is giving off these different kinds of radiation, they have to wear a badge like this. that counts essentially what kind of dosage they're getting. And then those badges are sent in periodically to check how much dosage people are getting so that they don't get too much. And if you reach your maximum, you have to quit that job. You can't do that job anymore. But even in nature, there are just radiation. There's radiation hitting us all the time. And so many studies have been done to help us to understand how much radiation we're getting, and that's what this top line in this chart is about. Natural radiation from external sources, cosmic rays. If you're in Australia, you're getting 0.38, Germany, you're getting 0.28, the United States, 0.38, in average in the world, you're getting 0.39. Soil and building materials can give you a dosage of radiation, just exposure to these things. Radon gas, look how much it goes up if you're around radon gas. Internal natural radiation from things that we have in our body. This is stuff we get just by living, right? Different things that we ingest in our body, carbon-14, radon, and potassium. Potassium, I got a banana in my office that's radiating potassium because it has potassium-40 in it. If you're in a dental office, these are the things you're getting, right? Why is it so much lower in the United States? Well, in the United States, we encourage people to take care of their teeth better. We probably have the best teeth in the world as far as that goes, and so people don't have to be irradiated as much. They don't have to be x-rayed as much, right? And also we have better equipment. The new x-ray machines that we're using in the United States are digital x-rays, and they only require a very small burst of radiation, so you get much less exposure. And so you can see here that you're getting different doses of radiation just by living in the world. We're actually higher in the United States than average because of natural internal radiation from things that we're eating, and also higher in the radon gas category because we have more radium in our soil. So it's just a natural consequence of living in the United States, unfortunately. Here they talk about different radiation doses that you're going to get in different medical procedures. Chest x-ray, 0.02 millisieverts. Dental x-ray, 0.01. It's even lower nowadays. And many of these are lower since the advent of digital x-rays. But you have skull, 0.07, leg, 0.02. Why would it be so much higher for a skull than it is for the chest x-ray? Yeah, it actually takes a bit more to look through it. You have to expose it for longer to higher energies just to get through the skull. It's thicker bone. But a mammogram is even higher. Why is that? Well, it just so happens that the tissue of the breast is more susceptible. So remember that the sievert is affected by that biological effectiveness thing, right? So, go back up here, where is it? So right here we have our, I can't remember what it is, relative biological effectiveness. So that is a factor that is determined by not only the type of radiation, but what is it going through? Right? What kind of tissue is it affecting? So you have to take that into account as well. Barium enema, the upper GI X-ray. I had one of those myself. CT abdomen, which I actually had. That's a big one. I had a CAT scan of my abdomen not too long ago. So that's a big dose, and they put that in your medical records so that they know how much radiation dosage you have medically over the course of your lifetime. Because it comes to a point where they just really have to be careful with that. So, let's calculate a dose. We're going to calculate the dose in rems per year, it looks like, for the lungs of a weapons plant employee who inhales and retains an activity of 1.0 microcuries of plutonium-239 in an accident. and there's 2 kilograms of lung tissue affected, and it decays as an alpha particle at 5.23 mega electron volts. So there's our energy. We've got our energy, we've got our activity, the millicurie, microcurie, we have our mass, right? And we're going to assume the higher value of the RBE for alpha from the table, the RBE table, okay? So, first of all, we are going to calculate our activity. Our activity appears in microcuries, but remember that microcuries, for every microcurie, there's going to be 3.7 times 10 to the 4th becquerels of activity, because it's 3.7 times 10 to the 4th times 10 to the 7th rather for millicuries, right? So you have to take 3 off of that to make it 3.7 times 10 to the 4th decays per second for 1 microcurie. So that's our decays. The number of decays per year, we're just going to do a conversion to years. So if we have this many per second, there are 3.16 times 10 to the 7th seconds per year. So we multiply those together to get 1.17 times 10 to the 12 decays per year. The ionization energy that's going to be deposited every year is going to be, each one of these is going to give off 5.23 mega electron volts. So you have to multiply this huge number by mega electron volts here. And so once you do that, then you convert the mega electron volts using 1.6 times 10 to the minus 13 for joules per megavolt, and then 0.978 joules is the total amount of energy deposited in the tissue. So we take the energy divided by the mass, which is the definition of the dose, essentially, and you're going to get 0.489 joules per kilogram, right? Remember that a gray is joules per kilogram. Why did they do this? That's kind of goofy. A gray is joules per kilogram, so this is the same thing. So you just transferred down. I don't know why they did that, but it's kind of goofy. But anyway, you can just say that this is grays because it is joules per kilogram. And then in sieverts, we take that number of grays times the relative biological equivalent, right? Which in the higher one for alpha particles. And so it was 20 for alpha particles and protons, and we get 9.8 sieverts for that dose in sieverts. And what kind of damage did that give us here? So that's 9.8 per year, right? Is what it is. So 9.8 sieverts over that course of that year. So that could be these are single exposure effects. So if that happens over 1 year, then it probably isn't going to be as bad. But still, probably there'll be some effects. Anyway, that's kind of the idea of calculating dosage and dosage of radiation. You have to know the energy, you have to know the activity, and you have to know the RBE and the mass being affected. So, can it be useful, this dangerous radiation? In fact, it can be. So one of the ways this is useful is to kill off things that you don't want in your body. For example, tumors. If you have a tumor in the body, you can actually point these different sources of radiation at the body, and they will penetrate the body, and they will have some effect on the body where they go into the body. But if it's a low enough dose for each one of these cameras separately, it's okay, because it's only going to affect you along the line of fire. However, if you aim them all towards one spot from different directions, so that they only overlap at that one spot, you're going to get triple the amount of radiation, but only at that spot where they overlap. This is especially true of gamma rays. Gamma rays only can run right through each other without causing any effect to each other. Mostly the other ones can too, but they don't penetrate as deeply. But gamma rays go right through, and where they overlap, you can get triple the amount of radiation, and you can kill off that radiation. And sometimes you can't kill it off all at once because it would be too much of a radiation dose for the patient, and make them sick. So what they do is they do a little bit at a time. They'll do a little bit today, and then they'll wait a week or two, and then they'll do a little bit. And they give the body time to recover. They give the white blood cells a chance to recover. They give the other things in the body just a chance to rebuild themselves and to overcome the effects of the radiation dose. And then they do it again, and they kill off the tumor a little bit at a time. And this is what is referred to as radiation therapy, or radiotherapy. Another thing that they can do is they can actually put in seeds, and I think we talked about this a little bit. Let's just go look it up really quick. Radiotherapy seeds. So they kind of look like this. These just tiny little things, and they're made of a radioactive material that's been put in a radioactive environment, like a nuclear reactor. Thank you. My brain just turned off. But anyway, then these can be inserted into different parts of the body that have cancer and that you need to kill off. So they put them so you can see an X-ray with all these in here, and these have been put in here in different positions and in different orientations on purpose to kill off this specific tumor. So so they know exactly where to put it, and this is for prostate cancer. They put it in there to kill off the tumor in prostate cancer, and they can. These are all of these are for prostate cancer. It looks like. But you can see different pictures of these things. They're just these tiny little seeds, and they can use them all over the body, not just in prostate cancer. But the idea is that each one of these things gives off radiation, and a certain amount of radiation in certain directions, and they know which directions and how much, so they put them in there. If you have more cancer, they'll put more of them in there. If it's a bigger tumor, they'll spread them out more, and turn them in different directions to give more radiation in one direction than another. And then eventually, they actually will just become not radioactive anymore. Eventually, they'll lose all their activity, or most of their activity, and they won't be radioactive anymore. But that is designed, they design them so that they lose radioactivity when the tumor is dead. So they put just enough in there to kill the tumor. And hopefully when they're dying out, so is the tumor. And then they can either remove them or they can dissolve in the body, depending on what they're made of. So those are radiotherapy seeds. And they do both of these kinds of radiation therapy here at this cancer place here. Here they have a little components of thing. Here we have porous ceramic, titanium on the outside, the gold X-ray marker on the inside so that they can find it. They put a little piece of gold in there so they know exactly where it is. So they can see where it is. So anyway. I'm hoping that they show it using it in another kind of thing besides prostate cancer. Prostate cancer is probably the most common place that they're used, but they are used in other things. Here's the probe for putting it in. Doesn't that look lovely? Not a pleasant thing, I'm sure. Anyway, so radiotherapy, let's also look at, I think that they show this here later, hold on. So here's the doses that you need to kill off different kinds of cancers, typically. For lung cancer, 10 to 20, Hodgkin's disease, 40 to 45, skin, 40 to 50, ovarian, breast cancer, brain. You can see some of these are much higher than others. Here they have just a little note at the end talking about chemotherapy. Chemotherapy achieves the same result, the same thing by killing off cancer cells, but they do it a different way. They use chemicals, so that it's essentially drugs that they use. So oftentimes people confuse chemotherapy with radiotherapy. Chemotherapy has the same also side effects. In radiotherapy, you often kill off fast-growing cells, so white blood cells, but also hair. So you often have a loss of hair with radiotherapy, particularly if you're having radiotherapy near and around your head. But chemotherapy does the same thing. It kills off fast-growing cells and often can kill off the hair and the white blood cells. So they have kind of the same side effects and many of the same symptoms of illness that the patients have to endure as they go through this. And really what it comes down to is you're trying to kill off the disease just slightly faster than you kill off the patient. But that's the case with so many things. That's the case with almost all medicines. Every medicine that you take has side effects. And what you're hoping is that you can take enough of this medicine to get yourself better, but not so much that you kill yourself with the side effects. Because just about any drug that you take, if you take too much of it, it'll kill you. There's not many drugs out there that aren't designed that way. It's kind of a standard form of medicine. This one is just a little bit more extreme, and so it gets a bad rap. Chemotherapy and radiation therapy get a bad rap because they're more extreme routes, and they have more extreme effects on the body, and so people are afraid of them. People are leery of them. And of course, it's not a good thing if you have to go through chemotherapy or radiotherapy, because they are kind of that medicine of last resort. But they're still the same kind of medicine, and very well controlled by the doctors. They know what they're doing. They understand the risk, and they understand what they're trying to accomplish. So, in the end, it's very effective. It's extremely effective. Food radiation, free radicals. So we also use radiation to kill off bacteria in foods. They also use radiation to kill off bacteria and viruses, I guess, also. It's used all the time in the food industry. The thing that people kind of freak out about are the side effects of the radiation on the food that we eat. Is it killing off important things that we need in our food? So that's the free radical idea. There are things in our foods that they call free radicals, which can be destroyed by radiation, and those free radicals are important for our health. And so the more irradiated food we eat, the fewer free radicals we get in our diet. So essentially, if you're buying all of your vegetables from Walmart, almost every vegetable from Walmart has been irradiated. Why would they do that? Why would they irradiate food, especially fresh food? I'm sorry? So it lasts longer. Where does Walmart get its lettuce from? California and Mexico. Okay? The two places that can grow lettuce all year round. Pretty much the only two places that can grow lettuce year round. So they get some from Texas as well, but still, it's days away from here. And they have delivery spots in between that they have to drop it off at. And so the lettuce that you're buying at Walmart is at best 4 or 5 days old. But lettuce won't last that long once you cut it. Lettuce will maybe last 2 days. Maybe, and it'll be in bad shape. So in order to get lettuce all the way to North Platte at Walmart, you have to kill off all of the bacteria that's causing it to die, or most of the bacteria that's causing it to die. And that's what they do with the radiation. They do it on all the foods. It's the same. Some foods do better than others. Apples last longer, potatoes last longer. But tomatoes, not so much. They don't last so long. And lots of your green leafy vegetables and other things like that just don't last very long. So they have to irradiate them, otherwise they won't be able to ship them. And that's really changed things in the past probably 50 years when it comes to food. Is the irradiation makes it last longer. They also irradiate eggs and meat. The reason for irradiating eggs and meat, of course, is that eggs get lots of bacteria on them because they get lots of chicken manure on them. And chicken manure is full of bacteria. Chicken manure loves E. coli and what's the one? Salmonella. Yeah, all those things get on egg shells. The egg inside the shell has no bacteria in it at all. There's one cell inside of an egg, and it is the egg. It is the chicken reproduction cell, the female chicken reproduction cell. That's the only cell that's inside of it. There is no bacteria, there's no virus, there's no nothing inside of it. It's on the outside that's the problem, so they have to irradiate them to keep them clean. And that's also why we have white eggs in America. The reason that Walmart sells white eggs in America is because you can tell if a white egg is clean. You can't tell if a brown egg is clean. That's the real reason. White eggs can be cleaned, and you can tell if they're clean when they're clean. And they have to have that, otherwise they get sued. They get sued for everybody that gets sick from an egg sold at Walmart. So they keep them clean, they keep them irradiated. So there's a lot of this science goes into food to make sure that these companies do the science so that they're covered legally, but also so they can sell it so that it looks and smells fresh, even though it's not, And but the downside is that free radicals. Free radicals are also killed off during that part, and we need those things. We need the nutrition that comes from free radical molecules. I don't know the exact definition of free radicals, but I think they're something like, they're kind of like vitamins and things like this. But anyway, so there is some loss there, but still, I think the good that comes from having those vegetables in places like Nebraska in the winter is far better than the bad that we have to deal with. In the summer, of course, you can get your vegetables out of your garden and be healthy, and which is what I do. But, anyway. So now we're going to talk about nuclear fusion, and nuclear fission. Nuclear fusion, nuclear fission. Starting with fusion, because fusion is what makes the sun shine, right? So what's going on with nuclear fusion? It's a Here we go. It is a process in which hydrogen becomes helium. So you start off with two hydrogen atoms, and they come together, and they go, and one of the hydrogen atoms, one of the protons, goes through a decay. And as it goes through decay, it creates a neutron, a positron, and what's called a neutrino. And through this process, the neutron and the proton from the other hydrogen become what we call deuterium, which is one of the isotopes of hydrogen. And then it does it again. This deuterium does the same thing again with another hydrogen. And why would it do this? Because it turns out that deuterium is actually pretty stable compared to just plain old hydrogens, especially in a high energy environment. When there's a lot of energy in the environment, these deuteriums like to hang out together. They like to come together. And this actually releases some energy. It releases 0.42 megaelectron volts per reaction. And then becoming tritium also releases some energy. But this is the biggie. These tritiums are not as stable as helium is. So they will actually, two of these will get together and create a helium nucleus, releasing two protons. And when you create that helium, it's very stable. And so it has much lower energy and releases 12.86 megaelectron volts of energy for every helium atom you create. Hydrogen, not stable. Helium, very stable. Okay? Particularly in high energy environments. In a high energy environment, hydrogen is just not stable. In any environment, it's not stable. You know, it's extremely combustible. So just give it a little bit of a match light, and it'll explode with some oxygen. But helium is extremely stable. And once you make helium, it stays helium. It doesn't like to do anything else. So going from hydrogen to helium is not a huge stretch. And this process is called the fusion process. In order to do it, you have to have some energy available to start the process, but in the end, it releases more energy than it absorbs. And so it creates an energy surplus. And that energy surplus is what makes the sun shine, what makes the sun hot, what makes everything in so it makes everything in the sun. So, anyway, so this is what it looks like from beginning to end. You have 2 electrons, 2 free electrons, 4 free protons, and when you go through this whole process, you end up with 1 helium, 2 neutrinos, and some gamma rays coming out, 6 gamma rays coming out. Because notice in the second process, there's a gamma ray popping out there. In the end, what happens is you get, if you have enough of this happening, you get a star, and they're actually at the Fermi at Fermi Labs, which is just outside of Chicago. They have this pool. What you're seeing here is you're looking down into a pool of deuterium. It's called heavy water. So it's water that's made, instead of made with hydrogen, it's made with deuterium. So it's slightly different than water. And as neutrinos come down through from the sun, these neutrinos that are popping out of this reaction here, as the neutrinos come from the sun, they interact with the neutrons, the extra neutrons in the water in this pool, and then they create these flashes of light that are detected by these photomultiplier tubes at the bottom of the pool. It's very difficult to detect neutrinos. This is one of the only methods to detect neutrinos. Another method for detecting neutrinos involves using the Earth to detect them. You actually have these photomultiplier underground in caves. And they're just very difficult to detect. And so this is one of the reasons that we think that neutrinos might be what dark matter is. Because they're so hard to detect, we can't see them out there floating around in the universe. But it's possible that dark matter is composed at least partly of neutrinos. Supernovas. So everything up to iron in the periodic table is built inside of, is built from nuclear fusion inside of the stars. Essentially, you have, as you go further out in the layers, you have different reactions going on that are building, a few different fusion reactions that are going on, building bigger and bigger molecules, or bigger and bigger atoms. And then those atoms are released out into the universe in the form of gases, usually, by the stars. But anything heavier than iron, so you go down here to iron, which is, where's our iron? Where's iron? Here it is. There's some of them. So iron is right here, and it has 26 protons. Anything bigger than that, all these out here, and all these down here, all the way up to uranium, are created in supernova explosions, where a star collapses and then explodes because it can't support itself. It doesn't have the right balance of mass and size and gravity and everything else. Then when that happens, you get a huge fusion reaction that creates these larger things, and as it expands out and cools and releases its energy. Then we move on to, so this reaction that we saw up here is the one that goes on in the sun. It's called the proton-proton cycle. And if we wanted to make energy using fusion, this would not work. It's not efficient for us. It requires too much energy to make it happen. It's called hot fusion. It requires so much energy that it's just not, we just wouldn't use it. But we could use this cycle. This is, instead of two protons coming together, we start out with deuterium. So we start out with hydrogen 2, start out with deuterium, make your tritium, and start out with deuterium and make helium 3 as well. So you go deuterium, deuterium to helium to hydrogen 3, deuterium to helium 3. And then you can do deuterium and hydrogen 3 to make helium 4, and 2 deuteriums to make helium 4. So it's a different reaction in the end. It actually takes, it's a longer reaction, but it takes less energy to start it. And so it's called cold fusion. The problem is that we haven't been able to, the problem is we haven't been able to make this reaction happen, this fusion reaction happen, and get more energy out than we put in such a way that we can actually make money making this power. So we have been able to make this fusion reaction work and get more energy out than we put in, but not enough energy out in order to make up for all the energy we had to put in. So that's the problem with it. They're constantly trying to make this happen. The most promising way of doing this is using magnetic confinement in some kind of a usually it's some kind of a rotational environment where the reaction takes place in a toroid, and a toroid is essentially a donut, and the plasma that's created during this process, or kind of like the star, is being spun around and around inside this toroid. And the reason for that is because you have to keep it at a high density. So you have to squeeze it and keep it tight. And they do that using magnetic fields. Because a lot of the parts involved in this reaction are neutrons, you can't confine them using light or electric fields. Electric fields don't affect neutrons because they have no charge. So you have to use magnetic fields because they do have a magnetic spin. So you have to combine them using magnets. Now this thing is much bigger than it looks. This is just a model of it. But if you look at the ITER reactor in real life, it's huge. So let's see if we can get one that shows its actual size. Here we go. So this is the inside of one of the ITER reactors. You can, as one of these workers can easily stand up inside of the reactor. On the outside of the reactor, it's much, much bigger. This kind of shows it, but not really well. It's just a model. Let me show you. This shows you the size of it. So here's a building where they have little tiny buildings and trucks down here. So it's huge. And the size of this is all because of the magnetic confinement coils. Magnetic confinement coils are monstrous. Here, this is just the bottom of the reactor. But what are they? What? What they're trying to do is create that fusion reaction inside of the reactor. So here, here we go. So coming up around this thing are these electromagnets. So there's huge coils of superconducting magnets, and then the plasma goes around and around and around here and goes through its reaction it essentially turns hydrogen into helium, and then it releases a ton of energy. And that energy can be used to make electricity. So that's what they want to do with it eventually. The upside to this being that you get a lot more energy out of this than you would out of a nuclear reactor. So it could give a lot more energy in a lot smaller space. The other thing is it doesn't require any fuel except for water, essentially. I mean, all it needs is hydrogen, which you can get from water. And we've got a lot of water on this planet.
So the goal is to replace the nuclear reactor?
So we wouldn't have to use radioactive materials.
Like a new energy source?
Yeah, it's essentially a new. This is the energy source of the future. It's a nuclear process that doesn't require uranium or plutonium or something like this. It just requires water. You split off the hydrogens from water and you're done. You've got your fuel. Your fuel is hydrogen is the most abundant thing in the universe. And you've now got a fuel that is the most abundant thing in the universe, whereas uranium is very rare, and so is plutonium. You don't need a lot of uranium and plutonium, but it is very rare. And it's kind of dangerous to work with, right? You can get a meltdown in a nuclear reactor. In this reactor, if something goes wrong, it just turns off. And you're done. It doesn't turn into some bomb or something, right? With the nuclear reactor, it can turn into a bomb. So you have a lot fewer problems that you're dealing with here as far as dangers. The one danger that is a huge problem with this one is neutron radiation. Because you're dealing with free neutrons at high energy, you have neutron radiation, which is extremely difficult to stop and extremely damaging. It causes damage to metal. The metal inside of this thing gets destroyed. It's constantly being replaced. And that's what this shielding is inside of here. So here you see the ITER reactor when it's not on. This is what it's on. And you can actually see this little layer of plasma, which is essentially like fire from the sun. Okay? Well, that plasma is made up largely of free neutrons at high energies that are just going to bombard this metal. These metal plates in here are just shields to protect sensitive equipment and to protect the people on the outside from this neutron radiation. So the neutron radiation can be really, really bad, but it's really, but it's much less really radiation than you get from normal nuclear power. Let me show you a before and after. ITER. What's that? Field? That's not what I'm looking for. ITER damage. There we go. Here's a nice picture of a damaged plate there. But here they have a really good picture of it, hopefully. Here they are taking pictures of it all cracked up and broken up at very close range. Here it is at further range. You see these cracks in the shielding here. That's due to neutron bombardment damage. Let me see if I can. They used to have a really great picture of before and after on the wall. Let's see here. No, that's all. You can tell when it's good, when it's in good shape, because it's all shiny. The after pictures are the ones that are really obvious. This one you can see a little bit of damage. It's not nearly as shiny, but it's not terribly obvious. In some pictures, it's so obvious it's just not even funny. Like this one is all brand new plates. You can see. But afterwards, it's essentially all the shine is gone to those plates, and they're just beat up. They're just really beat up. I don't have any great pictures of it here. And there's not just one of these in the world. There's several of them around the world. So we're kind of, this one actually shows some of the damage, but that's the reason every time I open up a new one it looks slightly different, is because there are several of these reactors all over the world where they're doing research and every one of them slightly different on the inside. The overall concept is the same, but the insides are all slightly different. But there are some that are really different. There's one that's a twisting toroid. Instead of being a very symmetrical toroid, it actually rotates. So it rotates in 3 dimensions, so it's kind of cool. But anyway, this is a fusion reactor that hopefully will provide us with limitless energy for the future. Once we get these things where they're at a breaking, once we get this process to work, where it's affordable enough to replace nuclear power or coal power, it's probably never going to be cheap enough to replace coal power, but if you could replace nuclear power with it, which is a little more expensive than coal power because of regulation, then you could certainly do some interesting stuff with it. Now, did we talk about the National Ignition Facility?
Yeah, with the photons being.
With all the lasers?
Yeah.
And so that one, they're doing fusion instead of confining it with magnetic confinement and causing the reaction to happen. They just make a star. So they just bombard a pellet of deuterium and tritium and then create helium by squishing it with the lasers. So in this example, they want us to calculate the amount of energy released when we create helium from deuterium and tritium from that particular reaction where you have helium-2 and helium-3, or sorry, hydrogen-2 and hydrogen-3 creating helium-4 plus a neutron. The energy per reaction is 17.59 mega electron volts. What if we have a 1 kilogram mixture of deuterium and tritium? Which means we have to have half and half equals 1 kilogram, right? Well, you go to your periodic table and you figure out how much helium-2 is how much it's going to have. It's going to have a 2 atomic mass units mass. Tritium is going to have a 3 atomic unit mass. And so it's going to have a total of 5 per reaction. So 5 atomic units. A mole is going to be 5 grams. So how many moles are you going to have in a kilogram? You're going to have about 200 moles in a kilogram. And so that's what they calculate here. It's about 200, 198.8 exactly if you actually do the calculation of 1,000 divided by 5.03 grams per mole. That means you have 200 moles essentially of stuff. A mole is 6 times 10 to the 23rd. So you're going to have number of reactions you're going to have is 1.2 times 10 to the 26 as you multiply these two together. So a big number of reactions, and the amount of energy per reaction is 17.59 mega electron volts. So you multiply that together, and you get and make the conversion from mega electron volts to joules. You get 3.37 times 10 to the 14 joules. So for 1 liter of water, essentially, you can think of it as 1 liter of water, this much hydrogen. Okay, a box full of liquid hydrogen, if you can make it liquid, which you can, but would give you 3.37 times 10 to the 14 joules. The amount of power would be 10.7 megawatts. Okay. That's a lot of energy. All right, so now we're done with fusion. Let's move on to fission. So fission is just the opposite of building bigger atoms. It's taking a big atom and splitting. And of course, we saw that in our video. We learned about how that works. You go from uranium to strontium and xenon when you start with uranium-238. Now, uranium-238 will go through a fission reaction, but it will not support a chain reaction. And the reason that it won't support a chain reaction is the neutrons coming out are not high enough energy. And there's not, so essentially you're not going to get, you're not going to build a bomb with uranium-238. But you can build a nuclear reactor with uranium-238. So it can split into strontium and xenon and 3 neutrons, and then you're good to go. But, and in fact, this reaction and the 235 reaction create enough energy so that uranium that is mined from the ground is actually warm to the touch because of the energy that it's creating from its fission reactions. So there's fission going on all the time in uranium, and you can actually feel the result of that fission by touching the uranium.
Now, how do we calculate the amount of energy? Remember the mass defect? The mass of the reactant, excuse me, is greater than the mass of the products. So if you start off with the mass of uranium-238, it is about 238. It's 238.050784 atomic mass units. But if you take the mass of strontium and the mass of xenon and the mass of the 3 neutrons and add them together, you get 237.866. Almost, we're talking so this is 0.16 and that's 0.05. So it's about 0.2 atomic mass units have been lost in this process. And the loss is in the energy that's released. So it ends up being 0.183791 units of mass lost, or this is called the mass defect. And to calculate the amount of energy, pure energy that's released, so that pure energy can be in the form of gamma rays or heat or blast or pressure expansion or whatever else. But that energy that's released is measured by E equals mc squared. So you take that delta M, put it in your equation with c squared, and we're using c squared equals 931.5 mega electron volts per c squared per atomic mass unit. So it's a funky way to say the speed of light. But once you've multiplied those two together, you get the amount of energy that's released, which is 171.2 mega electron volts. So every time uranium-238 goes through a fission process, it releases this many mega electron volts of energy. Neutron-induced fission reaction. So this is the reaction that happens with uranium-235. Uranium-235, this one up here just happens. Uranium-238 just happens. It doesn't require any energy, it just happens because uranium-238 is not stable, and so it just goes through this reaction on its own and decays to become strontium, xenon, and 3 neutrons, and releases some energy. This one down here is a neutron-induced fission reaction, which is what happens inside the bomb, where you fire in a neutron at uranium-235, and you end up splitting it into barium and krypton, and 3 neutrons that are very high energy. And then those neutrons coming out can hit other 235s and create a chain reaction because it is neutron-induced. So there's the idea of the chain reaction and everything else. And then, of course, you can build a nuclear reactor if you harness that energy that's released. Now, how do you control this reaction inside of a nuclear reactor? Well, you use what are called control rods. Inside the nuclear reactor itself, you have these rods that are the fuel rods that just have little pellets of nuclear material. I actually have some simulated nuclear reactor pellets here. That's what it looks like. It's uranium, and it's about that size, about the size of the end of your pinky finger. Right? One of these things is equal to 1 ton of coal. You burn 1 ton of this stuff, so essentially a large truckload of coal is equal to burning one of these things, or using one of these things as it goes through its reaction. It's equal to 149 gallons of oil and 1,700 cubic feet of natural gas. So it's a very, very small amount of fuel for a big amount of energy. But you put those in fuel rods, and these fuel rods will hold thousands of these things. So let's take a look at what a fuel rod looks like. It's quite large, actually. So here are the actual fuel rods. Here's a picture of the fuel, not a picture, but a diagram. So you have these rods, these round rods that are just stacked with these fuel pellets, and it's got this cladding around it made of metal. And inside in the fuel rod, there's many of these things, and they're only about this big around, not very big. But then they put a bunch of them together in what's called a fuel bundle, or a fuel assembly. So that's the fuel assembly. Let me see if I can find. We actually held a simulated fuel assembly when we went there. You remember that? Remember when we picked up that fuel assembly and took a picture with it? I have it on my camera somewhere. I'm looking for an actual photograph of a fuel rod. Here's an actual photograph of it. So here is the here is a fuel bundle. And sometimes this one is hexagonally shaped. Sometimes they're hexagonal. Sometimes they're square. Sometimes they're round. But essentially, it's just a bunch of these things all put together, right? So they've got these huge things, and these things can be as big as the reactor, 20 feet long, maybe 10 feet long, whatever. But they can hold thousands of these fuel rods in them. But then they put in the control rods. So let's see here. Let's see if I have a diagram of the control rod. Yeah, so here are the control rods, and here is the control assembly. So you've got all your fuel rods here, and then you've got this other thing that inserts these control rods in between the fuel rods, and it's shown in different places. Here's another one. And each one of these control rods is made of materials that absorb neutrons. So if you put in the control rod, you stop the neutrons from going from one fuel rod to another to create the chain reaction. The control rods stop those neutrons and prevent the reaction from getting too hot. So you can put in the control rod slowly to control the reaction more. If you put it in deeper, it cools down the reactor. If you pull it out further, it heats up the reactor, essentially. It makes the reaction happen more. But if you want to stop the reaction, you just drop those control rods in all the way. And then you flood the whole thing with water, if it's not already flooded with water. So the control rods are in between the fuel rods. Oh, here's a cool picture of a spent fuel storage pool. This one's in Tokyo. 6,840 fuel rod assemblies can fit in the spent fuel pool. Anyway, so that's the basic idea of fuel rods and control rods inside of nuclear reactors. You have the fuel rods that hold the fuel pellets, the control rods that go between them to prevent, to control how hot it is. Here you can actually see the control rods in action here. They're going in and changing the reaction rate by blocking neutrons. Putting these things together is a big deal. It's one of the big jobs that nuclear scientists have, nuclear engineers have, is actually assembling new fuel rods for use in nuclear reactors and designing fuel rods for nuclear reactors. So, but you have fuel rods and control rods, fuel rods and control rods. So anyway, as and here they're showing them as separate, there's very few, but there are lots of them. But anyway, as you put them more in, as you put them further in, it gets cooler. You pull them further out, it gets hotter, and then you can control how much energy you're making. And also in an emergency, you can just drop all the fuel rods in and shut down the reactor and prevent it from doing anything. So, calculating the energy from a kilogram of fissionable fuel. So we already did a kilogram of hydrogen in fusion. Let's do a kilogram of uranium in fusion. So for each atom each atom gives off a certain amount of energy, and the atom per unit was 23 or something like that. We got, what was it? 1,000 grams, 6.2. Here it is. The amount of energy that was given off per reaction is right here, was 200 mega electron volts per 235, per uranium 235. 200 mega electron volts. Turns out that you get 2.56 times 10 to the 4 uranium atoms per mole here. Then we do a conversion here, and we calculate total amount of energy released. But notice that it's much smaller than the the amount that was released by fusion. Fusion was 4 times that. For a kilogram, so for a kilogram of hydrogen and a kilogram of uranium-235, hydrogen gives off 4 times as much energy as the uranium-235. A kilogram of uranium-235, that's so difficult to come across. It's so rare, but a kilogram of hydrogen, getting that in your shower every morning, easy. So anyway, here they do some other ones. Uranium-239, or this one's uranium-238 rather. Oh, sorry, this is not what I was thinking. This is actually the making of plutonium is what they're doing here. I thought they were doing a different fusion reaction. There are several fusion reactions for everything that it goes through. Several fission reactions rather. There's not just one. But anyway, I thought they were doing a different one, but they're actually doing breeding. So this is the reactor that can turn old fuel into new fuel. So one of the things that you get in natural uranium, and well, when you're mining uranium, is uranium-238, which will not go through a chain reaction, so it cannot be used as a fuel for reactors. It can be used as uranium-238 goes through its own reaction, its own fission reaction, but it's not a neutron one. So it can't go through chain reaction, but you can put a neutron with it. You can add a neutron to uranium, and then it becomes unstable. So once you add a neutron to uranium, it becomes uranium-239 in the top there, and then the uranium-239 decays because it's not stable, and it decays to neptunium. The extra neutron actually becomes a proton, decays to a proton, gives off beta particle, the electron, and the neutrino that we saw in the movie, and you get neptunium. And the neptunium does the same thing. It's also not very stable, and it will decay. One of its neutrons will decay to a proton, and then it becomes plutonium-239. Plutonium-239 does undergo fission in a chain reaction. So then you can use plutonium in your reactor instead of uranium-235. And uranium-238 is very common. It's not hard to find at all. It also is, the nuclear reaction is more efficient as well. It creates more neutrons when it goes through its nuclear reaction. So its chain reaction is much more efficient. That's why it makes more efficient bombs as well. Releases more energy more easily. So anyway, that's where we come to the use of this in weapons. So the very first weapon, which was a uranium-235 weapon, this was called Little Boy. You just had 2 pieces of uranium on either side, and they blew it, they shot it from one end to the other to create critical mass, and that critical mass underwent this fission process, just naturally underwent it because it had the ability to do so, and created the explosion. Pretty simple stuff. Plutonium, on the other hand, is you need less of it, and you can use this implosion method with it much more easily because it has a higher neutron release rate. It's easier to start the reaction, even if you don't have a critical mass. So you start with a piece of plutonium that's actually a subcritical mass, so it's very stable. It's not going to explode. It just sits there and it's warm to the touch. It's going through fission very slowly, but it's not going to explode on its own because it's not a critical mass, a supercritical mass. So what we do instead is we surround it with these shaped charges that are designed to explode inwards and crush it so that those plutonium atoms get much, much closer together. As they get much, much closer together, it creates a supercritical mass and then explodes as a fission bomb. And that was the second bomb that was made and the third bomb that was made. The second bomb was the one that they tested in the desert in New Mexico. The third one they dropped on Nagasaki. So there's the Trinity test. outside of Albuquerque, New Mexico. Los Alamos, I guess, is better. It's closer to Los Alamos. Los Alamos was pretty small at the time. And there's Hiroshima after it was bombed, pretty much decimated it. Of course, the damages done in Hiroshima and Nagasaki are a little bit misleading because they were Japanese cities. The Japanese built a lot with wood and paper. It was their primary building materials were wood and paper in most houses, most residential things. And so just about any residential building was just vaporized because there was nothing to it. Concrete buildings, however, survived fairly well. And you can see that the concrete buildings are still there. If more of the buildings were made of concrete or brick or something, you would see a lot more surviving buildings, but it's just not the case. So in the first bomb on Hiroshima, 80,000 people killed, 100,000 people seriously injured with one bomb. Pretty significant. And it was 15 kilotons of dynamite. It's equivalent to 15 kilotons of dynamite. They did drop flyers and said we're gonna bomb the city. So beware and leave the city. Written in Japanese so that they would know. But they didn't really believe it. They didn't really believe that it was going to be a problem because to that point, Japan was bombed early in the war, right after Pearl Harbor was bombed. The United States sent some planes on some aircraft carriers to bomb some plane factories and tank factories in Japan. But after that, the bombing in Japan was pretty minimal up until the end of the war. And so they didn't really believe that we had this weapon. And the government, didn't believe it. They were kind of holding out and they were in denial. So they just decided they would drop it anyway. The second one you can see 50,000 people, right? There are some reasons. There were more hills there, and also they didn't quite hit the spot they wanted to. But also, guess what? The Japanese knew what the first one did, so they left the city that time. That's the big issue. That was the big reason. People decided to leave the city after that and not hang on. So that ended World War II. And the casualties were as bad as people said, even before the bombs were dropped. There's a lot of politics about this still, and a lot of activists against the use of the nuclear bomb, saying that we were evil to drop the nuclear bomb, we should never have done, we didn't have to. It's not true. Even after they dropped the bomb, the Japanese would not surrender. After we dropped the bomb at Hiroshima, they refused to surrender. The Japanese government was willing to fight until the entire population was dead. The people flying planes were all under the age of 16 at that point. Japanese pilots were all under the age of 16. They'd been given a week of flight school, and they were sent up in planes to fight against the Americans. Americans were getting their aces in one flight. A pilot who had never shot down anybody before would go up and shoot down 5 Japanese pilots without even trying. And they were flying old planes that were, still made of paper. They were flying without weapons. That's when the kamikaze pilot came into existence. Kamikaze pilots weren't flying at Pearl Harbor. They weren't flying into boats then. They were flying into boats and into other places, other things, when they didn't have any ammunition or bombs left. And they were kids. My grandfather was actually in Hiroshima the day after they dropped the bomb to rebuild their hospital. And he had kids with guns trying to stop him from rebuilding their hospitals and disarming the people. And he had to, it was bad news. He had to do everything. He did everything he can to not have to kill kids. But plenty of kids got killed in that process because the Japanese government refused to give up. So finally, after they dropped the second bomb, they announced to not only Japan, but not only to the government, but all the people in Japan, so that everybody knew. They broadcast it to on every radio frequency and every broadband, everything that they could in Japan. And they said, look, we're going to drop a bomb every week until you surrender. One of these nuclear bombs every week until you surrender. It was a bluff. They only had enough plutonium to make one more bomb, and they hadn't even made it yet. You know, they would have had to wait a few weeks or even a few months to get enough plutonium to build another one after that next one. But they only had enough for one more. But it was enough, they'd made enough of an impression with these first two bombs that the Japanese government eventually did surrender in that following week and ended the war. But it really was as bad as history says it was. That's not a lot. And I have that from first-hand accounts from my grandfather who was there. It was really bad. And the Americans were not trying to just kill off Japanese people when they went there. They were very civil compared to what was going on in Europe. Very civil. So it was tragic, unfortunate and tragic. But
really sucks how the government put them up into a fanatical state like that.
yeah, but it's also a very cultural thing. You know, the imperial mindset is a very cultural thing in Japan. It's a very cultural thing in China. It's a very cultural thing in Korea. It's a very cultural thing all throughout Europe. The imperial mindset that we are the master race and we are going to take over. We are going to conquer the world. We are the best. And I'm not just saying that of just certain, the imperial mindset is a part of ancient cultures. And the two ancient cultures on this planet are in Asia and in Europe. Okay? There's no ancient culture in Africa, really. I mean, the ancientness of their culture it's just not that ancient. Okay? They have a lot of ancient people there. That, human races lived in Africa for a long time, but they didn't create a civilization that created this mindset of we're going to take over the world. They never did. The people in North and South America never created that mindset because we've not been around that long. And we were made up of people running from those people. Everybody that came to the South and North America were running from the imperialists in Europe. We were getting away from them. And so we don't have that same kind of deep-rooted superiority. But almost every civilization in Europe has that, not just the Germans. And not just the English, who are the most famous, or the Spanish and the Portuguese, who are the most famous for their imperialistic views. But it's very common in the old ancient Asian cultures and the old European cultures, and it drove that mentality. It wasn't hard for these governments to make it into a thing. It was already there. It's always been there. It wasn't Hitler that made Germans think that they were the master race. It just wasn't. It was a deeply ingrained, and still is, a deeply ingrained thing. It's very much a part of their culture. It's almost part of their DNA, you could almost say. It is, but it's changing. It's taken time, but it is changing. If you meet people from Germany now, you're very unlikely to meet somebody who has that mindset anymore. They're trying to, they're kind of beating it out of themselves.
Don't they like every year do like an international
Yeah,
policy?
they do that, and so the government is playing a big role in that. And this has a huge impact on science. And science has a huge impact on this part of sociology. For example, during these years where the European imperialists were taking over the world, they were the masters of military, they were the masters of economy, and they were the masters of science. Science was one of the things that they were the masters of. But it wasn't until this past 20th century that things started to change. Germany has not led science. England has not led science. Spain has not led science for 100 years. Who has led science for the past 100 years? The United States, the Americans. All the great inventions and all the great discoveries in the past 100 years, not all of them, but most of them, have occurred in the New World, North and South America. Okay, mostly North America, but both places really. Flight was invented at the same time in South America and North America. Okay, at the beginning of the 20th century, end of the 19th century. But you know, all these things, the electricity revolution, all these things took place mostly in the United States and South America, certain places in South America. But Europe has kind of fallen behind, and that has tempered this imperialistic view. It's tempered it a little bit. You still had it there. It was still present, but it's changed it a little bit. And if there was ever a Hitler to rise up again in Europe, I don't think he would be successful anymore, because I think it's mostly kind of gone out, and they're actually recovering in scientific ways. Now you have universities in Europe that used to be the cream of the crop of the world, and they used to be the leaders in everything. You know, when Einstein was around, all the great universities were in Europe, but that was 100 years ago when he was starting out. You know, that was 100 years ago when the United States was still kind of getting its feet under itself. But then after that, it was all the United States, and now it's all the great universities in the United States, but the European universities are making a comeback. And I think a big part of that is because that whole master race phenomenon has kind of been thrown out the window over the past 100 years. And a lot of that has to do with science. They saw that their science wasn't that great, and they gained a little humility, and they started to work hard again, instead of just assuming they deserved it, you know. United States, people in the United States, now we're at that point where we just kind of assume we deserve it. We kind of assume that we are the most powerful people on the earth, and so we kind of wonder if we're kind of in for a downfall. And it's kind of looking like we are, unfortunately. So politics and science and technology have a huge role to play with each other in each other's lives. And the bomb is the nuclear bomb is a kind of an interesting way to look at that, an interesting place to look at that.
So, with
if any of you need to leave, go ahead. You need to leave for class.
fearless that holding them back. What about what is America's ranking in science and math?
In what way?
Like
education-wise?
Is that just because we have a larger population and kind of?
As far as like, you know, how we do it, educating our kids, is that what you're talking about?
Yeah, I guess.
It's pretty low from what I understand. I don't know exactly where we're at, but that's not necessarily all that telling. We do have a large population. And the students that do get a good education in science and math usually go well beyond what most kids do in other countries, mostly because of the opportunities here. This is where the universities are. You know, if you live in Sweden, where they have a really good math and science rate, you have a very small population of people, so they're not going to put out a lot of Swedish scientists. But number two, you're in Sweden, where there's not that many universities where you can really get a great, you know, experience. So you're kind of lost.
So we might be lacking in like the pure
Primary education. Yeah.
primary education, but we take the top half. We take.
Yeah, they excel at the other end of the spectrum. For sure.
Oh.
Yep.